Hello everyone. In this lecture, we'll discuss about sparse matrices. Myself, Dr. Sminu Isuddin, Associate Professor, Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. This is the overview of today's lecture. We'll see what a sparse matrix is, some real-world examples, how can you represent a sparse matrix, and some operations which you can do using sparse matrices. What do you mean by a sparse matrix? Sparse matrix is a matrix with larger proportion of elements are zero values. That is, if you have a matrix with more zero values than non-zero values, then it is called a sparse matrix. Okay, so if you represent this matrix in the normal two-dimensional form, then it causes lot of wastage of space. For example, let us consider a matrix, a 100 by 100 integer matrix with only 10 non-zero elements. Remaining elements are all zeros. So only 10 non-zero elements means actually, since they are integer values, you need only 10 into 20 bytes to store them. But we are wasting 100 by 100 into 2, that is 20,000 bytes to store such a matrix. And again, if you want to access any element, you need to make 1000 scan to access these 10 non-zero elements. We can find many real-world applications where these sparse matrices are used. They are used for solving partial differential equations. And again, they are used for creating web page metrics. Now, web page metrics means assume that all the web pages in the internet, say you are numbering it from 1, 2, 3, etc. That is, if there are n web pages, let us number the web pages from 1, 2, 3, 4, etc. n. And I'm going to represent the information in the form of a matrix. I'm going to represent it as a n by n matrix, where n represent the number of web pages. Now, how I fill entry into this matrix is like, if there is, I'll count the number of links from page I to page j, and that will form an entry in my matrix wij or webij. So every entry, every ith j entry in my matrix will represent the number of links from page I to page j. So if I form such a matrix, then I'll call it as a web page matrix. Now it's having many applications. One application is stated here. You can do that in web analysis to find authority pages. Say authority pages means if you want to find out the pages that has many links to it. How can you find? You just take a row and add the values. You will get the authority page. You will get the count for every page. Now, if you visualize such a web page matrix, it is an example for a sparse matrix, because the number of entries, the number of non-zero entries will be very less. So we found that sparse matrix, if you represent in the normal 2D manner, it causes wastage of space. So you need some efficient method to represent them. There are mainly two methods: triple representation or array representation and linked list representation. So in the triple representation or array representation, we store only the non-zero values along with their row number and column number. That is, in this representation, we use a two-dimensional array, where you in your array you will have 3 columns, and the number of rows in your array will be the number of non-zero elements plus 1. That is, the number of rows in this array depends upon how many non-zero elements you have in the original matrix. And suppose there are n non-zero elements in the original matrix, in the sparse representation you will have n plus 1 rows and always 3 columns. Okay, and the first row we will dedicate to store some index values. That is, If you take the first row, first column in the first row stores the total number of rows in the original matrix. Second column in the first row represent the total columns in the original matrix, and third column in the first row represent the total non-zero values in the original matrix. And the remaining rows, that is remaining n rows where there are n non-zero elements in the original matrix, we'll dedicate one row for every or each and every non-zero element. That is, if you take one row, if you take any row, first column represent the row index of the non-zero element, second column represent the column index in the original matrix, and the third column represent the value, the original non-zero value itself. That is, first row, that is if you take a row, the first column will represent the row number, second column represent the column number, and third column represent the value, the non-zero value in the original matrix. It will be more clear when we see the example in the next slide. Consider the 5 by 4 matrix A given with only 4 non-zero elements. Now in the right side, matrix S represents the sparse form of matrix A. Now the first row, that is 0th row in matrix S, it represents the index. So the first or the 0th column in the 0th row, or the first entry, that represents the total number of rows in the original matrix, which is 5. And first column in the 0th row represent the total number of columns in the original matrix, which is 4. And second column in the 0th row represent the total number of non-zero elements in the original matrix, which is 4. Now there are 4 more rows. Each row is dedicated to each non-zero element. Now when you look at the original matrix A, the first non-zero element is 5. It is located in row 0, column 0. So that is why the row 1, first row, not 0th row, first row is dedicated to a non-zero element 5. So the first column in the first row is first 0th column in the first row is 0, because that represents the total number of rows. Then the first column in the first row is 0, because that represents the column number of non-zero element 5. And the last column in the first row represents 5, because that is the non-zero element 5 itself. Like that, the next non-zero element is 2, which is in row 0, column 3. That forms the second row, or second row, index 2, row 2 entry in the matrix S. Then the next non-zero element is 1, which is in row 1, column 3. And the last non-zero element is 3, which is in row 3, column 1. Next is a linked list representation. So here also we'll store only the non-zero elements along with their row and column index. And we represent it as a singly linked list where each node consists of 4 fields: the row number of the non-zero element, the column index, the value of the non-zero element, and the address to the next node. Since linked list representation is not familiar to you, we will discuss this topic in detail later. This is an example of a 4 by 5 sparse matrix with 6 non-zero elements. So we can see that it is represented as a singly linked list with 6 nodes, where each node represent the row index, the column index, the value, and the address to the next node. Even though we have 2 representation, in this lecture we will concentrate only on the array representation. This is a function to convert a given matrix to its sparse form. Now in line number 4, we are storing the total number of rows and total number of columns in the original matrix. Now line number 5 and 6, they are the loops to iterate through the original matrix. If an element is not 0, we are checking in line number 7. If it is not 0, then we are making a entry in the sparse matrix through line number 9, 10, 11 and 12. And finally in line number 14, we are storing the total number of non-zero elements. Now when you analyze the code snippet, we can find that there are two loops, that is in line number 5 and line number 6. Since there is a nested loop, the complexity of a function is O of n square. Now we'll try to perform some operations on the sparse matrix. First one is transpose. Now we know that to find the transpose of an array, we'll interchange the row and the column. That is, we change the rows to columns. So if you're given a sparse form of a matrix S, to form the transpose of S dash, we know that we have to arrange the elements in the order of their column, not order of their row. Suppose you are given matrix S. There are 3 columns. Let me name the column as column 0, column 1, column 2. There are the 3 columns, column 0, column 1 and column 2. So here column 1 represent the column numbers of the elements in the original matrix. Now I am going to arrange the elements in the order of their column, which means in the new matrix, in the transpose form, I should consider element 5 first because that falls in column 0. Next I should consider element 3 because that falls in column 1. Next I am having 2 elements in column 3. They are element 2 and element 1. Since I am having more than one element in the same column 3, I will consider their row index. So the row index of element 2 is 0 and row index of element 1 is 1. So what I will do? I will write 2 followed by 1. The steps to create a transpose matrix is given here. Suppose T represent the transpose form and S represent the origin or the sparse matrix. Now in the transpose matrix, I need to interchange the row and column compared to the sparse matrix. So that is the first thing. First you fix the row and column in the transpose matrix. Now what we have to do is we have to iterate through the elements. We have to iterate through the elements T times, where T represent the total number of non-zero elements. So you have to iterate. Now how many times you need to iterate? Here what we are doing is we are iterating these elements n times. That is, n represent the total number of columns. Suppose n represent the total number of columns in the original matrix, not the sparse form. Suppose n represent the total number of columns in the original matrix, which I will get from element entry S01. Then what I will do, I will iterate n times. What is the meaning of doing that? Each time I am searching whether the element with that particular column number exists or not. That is, I am iterating with some variable ranging from 0 to n minus 1, n times. So first time I will be checking whether there exists an element with column number 0. Next iteration I will be checking whether there exists an element with column number 1. Next iteration I will be checking whether there exists an element with column number 2. Like that I will continue till n minus 1. Now what I will do, iterate inside this, what I will do is we have to do this T times, where T represent the total number of non-zero elements. Okay, so during the first iteration with column number 0, I will go through all those T elements. I'll verify whether there exists an element with column number 0. If 0, I'll copy to the transpose matrix. If not 0, I won't copy. Next iteration, I'm searching for an element with column number 1. Again, I'll iterate through all these 3 T elements once again. This time, I'm searching whether there exists an element with column number 1. If so, I'll copy. This is my logic. Function to find the transpose of the matrix is given here. So in line number 3 and 4, actually we are copying the indices and interchanging them. Now in line number 7, it is a loop to pick the column number. Line number 7, look at line number 7, it is a for loop. The aim of that loop is to pick the column number. And in line number 8, it is again a loop to iterate through all the T elements one by one with that column number COL. So what you are doing is whether you are checking whether there exists an element with that particular column number COL. That checking we are doing in line number 9, that in if condition we are checking that. And if I find a match, then I'll copy the elements to my transpose matrix, but I'll change the row index and the column index. This I'll continue. So when you just go through this algorithm, we can find that there is a nested loop, the outer loop running n times, the inner loop running t times. Okay, so the complexity of the algorithm is O of nt. So in the worst case, what happens is suppose there are many non-zero elements, suppose all the elements are non-zero, that is a worst case complexity. So in that case, what happens, the total number of non-zero element t will be m into n, or the worst case complexity of this function is O of mn square. Next is addition operation. So you have to add two sparse matrices. Now given here are two matrices, two 4x4 matrices. It is written in a somewhat a sparse form, but by eliminating the first row or the 0th row where we'll store the index value. So here the matrix is written in the form where the 0th row is eliminated and all the non-zero elements are only written. Okay, so in the first matrix I'm having 5 non-zero elements. In the second matrix also I'm having 5 non-zero elements. Now to add these two matrices, the logic is we'll compare the row number. If the row number is matching, in the first case the row number, both the row numbers are 1. If the row number is matching, then I'll compare the column number. The column number, here the column number is different. Column number of the first matrix, the first entry is 2 and the second entry is 3. So which means 2 is less than 3. So I'll copy that entry which is 10. I'll copy that entry to the resultant matrix. So the first row in my resultant matrix will be 1, 2, 10 copied from the matrix 1. I'll advance to the next row in the first matrix because I already copied, but I will remain in the same row in the second matrix, which means I'm still in the first row. Now I'll be comparing, I'll continue the process, which means I'll be comparing the row number and the column number. Row number is same, column number of the element in the first matrix is 4, but the column number of the element in the second matrix is 3. 3 is lesser than 4, so I'll copy the entry from the second matrix to the resultant, which means I'll copy 1, 3, 8 to the resultant. I'll advance to the next row in the second matrix. Now both the matrices are pointing to the second row in the both the matrices. Okay, now we will compare the row number is 1, then the other side column row number is 2. One is row number itself is different, so what I'll do, I'll copy the smallest row number entry, that is I'll copy 1, 4, 12 to the resultant. I'll advance to the next level in the first matrix. So now we are in the third row in the first matrix, but we're still in the second row in the second matrix. Now I'll compare 3 and row numbers, that is 3 and 2. 2 is smaller. 2, which is the row number in the second matrix, is smaller. So I'll copy. They are different, and the entry in the second matrix is smaller. So I'll copy that entry, that is 2, 4, 23 to the resultant. I'll advance to the next row in the second matrix. That is, I'm in the third row. So I'm in the third row in both the matrix 1 and matrix 2. Now again I'll continue the process. I'll compare the row number. Row number is 3. Second matrix also row number is 3. I'll check the column number. Column number is also 3. 3, 3, both are same. So which means we will add. We will add the entries 9 and 5. Resultant is 14. So again, then I'll write to the resultant matrix. Now you have in the resultant matrix, I'll have the entry 3, 3, 14. Since I copied, I'll advance the row in both the matrices. Now we are in the fourth row in the first matrix. We are in the fourth row in the second matrix. Again, I can find that the row number and column number, they are matching. So I'll add the entries. I'll add 15 and 20. I'll get 35. I'll make that entry to the resultant matrix. So the entry will be 4, 1, 35. I'll advance to the next row in both the matrices because we copied from both the matrices. So now we are in the fifth row in both the matrices. I'll compare the row and column. Again, all they are same. We will add, and the entry is 37. This is how you perform addition. So to summarize the steps to perform sparse matrix addition, actually we'll iterate through the elements in both the matrices. We'll compare their index, and if their indices are same, then we will add and make an entry to the resultant matrix. But if their indices are different, then actually what we are doing is we are trying to find out which element will come first in the row when we represent them in the row major form, and that particular entry we are copying to the resultant matrix. Now we'll do this process until there exists element in both the matrices. Now if either of the matrices end up fast, we'll copy the remaining entries from the next matrix. This is the function to perform sparse matrix addition. So we know that the first step is we have to compare the elements in both the matrices. So that comparison step, that is what is given in line number 9. In line number 9, the while loop, actually we are checking whether there exist elements in both the matrices. Now once there exist elements, then we have to check whether they are same or different. If the elements are different, then we need to copy the elements in the order of their row major form. So which one will come first in the row major form? That is what we are checking in line number 12. And based on that, we will either copy from matrix A or will copy from matrix B. If both indices are same, then we need to add and copy. So that is happening in the lines 24 to 25, 24 to 30. And after that, if either of the matrix is over, then we need to copy the remaining elements from the other matrix. So the entry in the second matrix is over, then we need to copy from the first matrix the remaining elements in the first matrix. That is happening in line number 33 to 37. Else we need to copy from the second matrix. That is happening in line number 38 to line number 42. In this lecture, we saw what a sparse matrix is, what are the different applications, how can you represent a sparse matrix, and so we performed some operations. These are my references. Thank you.